Welcome to this lecture series in group theory. In this lecture, we will introduce the notion of a finite field, which is a central object in mathematics. And for us, it will be of importance because we want to see examples of groups coming out of vector spaces over finite fields. Okay, so let's get started. So I'm assuming that you are familiar with basic linear algebra. In particular, I'm assuming that you are aware and have dealt with the notion of an arbitrary field, even though in your typical first course in linear algebra, you're only introduced to or are working with real and complex numbers, and sometimes even rational numbers, but not beyond this. In my course on linear algebra, which is available on this channel, I have developed it in full generality, meaning everything that can be proven with the base field being completely abstract has been proven that way, even though all the applications and examples that we considered were always with real and complex numbers as their base fields. But everything was done in full generality, so you can instantiate those theorems for any field you like, in particular for finite fields, which we are going to discuss shortly. Okay, so even though I'm assuming you're familiar with this notion, let me still recall. So a field, as you must know, is a triple, where F is a set, plus is an addition, quote-unquote addition on F, which means what? Which means it's a function from F cross F to F, with certain properties that we will talk about. And similarly, this dot or multiplication is also a function from F cross F to F. So these two functions, they satisfy certain properties, which are what? Associativity. So addition and multiplication are both associative. In which order you add is irrelevant, and in which order you multiply is irrelevant. Commutativity. Whether you add alpha plus beta, well, I maybe misspoke a little bit about associativity. I shouldn't say in which order you add, I should have said, in what sequence you add maybe. So whether you add alpha and beta first and then add the result to gamma, or you first add beta and gamma and then add that result to alpha, it's the same thing. And here in commutativity, we are saying that the sequence of addition or the sequence of multiplication does not matter. Additive and multiplicative identity, well, we say that there is an element which we denote by 0 in the field or in the set F, such that this holds for all alpha, so it doesn't disturb any element if you add it to any given element. And similarly, there is one such thing for multiplication, which we denote by 1. Additive and multiplicative inverse. For each alpha in the set F, there is another element alpha prime, such that if you add alpha to it, you get 0. And how do we notate this? Instead of writing alpha prime, we notate this as minus alpha. Okay, and similarly, for each non-zero alpha, there is some alpha tilde, such that if you multiply alpha and alpha tilde, you get the multiplicative identity. And we denote alpha tilde as either 1 upon alpha or by alpha to the power minus 1. Okay, and distributivity. So the multiplication and addition, they behave well with each other, which means to say that if you multiply alpha to the sum of beta and gamma, you get the sum of the products. Okay, and I think this should brush up your memory, but again, recall, all these axioms are not some abstract garbage. They are just abstractifying what you see in rational numbers or real numbers or complex numbers. Think of them as models from which we have extracted some basic properties out, which are enough to develop most of linear algebra. Sometimes you want to also talk about things like inner products. So there you cannot work with an abstract field, you need some more structure, and that is provided by real and complex numbers. Anyway, so this was just a brief recall. I'm assuming you knew this. And examples, as we said, these are your fundamental examples. And then there is this non-example, the set of integers. Everything except this property is true for integers, right? So just an important non-example to keep in mind. In mathematics, we should learn by examples and by non-examples. When I was a student, I fell into this trap, which I think most people do, that the abstract definitions, the abstract theorems, all of these are the most important things to work through. But what is really more important is that you work with and through concrete examples. When you read a theorem, try to instantiate it in a concrete setting. That will help you understand the theorem better. You want to understand a proof? See the proof in a simple concrete setting first. That should illuminate or illustrate the main ideas of the proof, and then you can look at the full abstract proof. That way you can get a lot out of a proof. Anyway, so let's move on. Right, so let's talk about this particular notation. I discussed this in my recapitulation video also, but since I'm not assuming that you are familiar with this notation before coming into this course, I want to recall it. I think it is worthwhile to spend at least 2 slides on it. One thing let's recall is this congruence relation modulo n. Given any positive integer n, we can define a relation on Z, which we denote this way. There should be a subscript here so that we see the dependence on n, but we suppress it. We call it the congruence relation modulo n. And how do we define it? For two integers x and y, we write x congruent to y if and only if n divides the difference between x and y. And from modular arithmetic, you know that this is just kind of a shorthand notation of the following. This is really the full notation. So I could have very well said that we say that x and y are related under this congruence relation modulo n if and only if this holds, which means the same thing as that. So that much number theory I'm assuming, obviously. Okay. And now let me talk about this notation. So since we have a relation, well, not since, verify that this is an equivalence relation. So this is an equivalence relation. A small exercise. And once we know that this is an equivalence relation, we have the notion of equivalence classes. So Z mod nz is nothing but the set of all the equivalence classes. How do we read it? This is read as Z mod nz or Z mod nz. If you read Z as Z, this is Z mod nz. Okay, that's how we pronounce it. And what is the definition? This is the set of all the equivalence classes. Under the congruence relation modulo n. Right, so that's sort of an abstract description. We can very explicitly describe it. So we can say that Z mod nz is nothing but the following set. So we are saying Z mod nz is this set, but what does this mean? I have to explain. First, let me define what this means. This itself means something. What does it mean? It means all the multiples of n. It's a good notation, as I'm sure you appreciate. This is all the multiples of n. And what is this? This is the offset of all multiples of n by a. Right? All right. Again, this is also a very good notation. And here is an exercise for you. Show that a plus nz is equal to b plus nz if and only if a is congruent to b modulo n. Very simple exercise. Okay. Maybe I'll put it here. This is put it as an exercise. And having done this exercise, once you do this exercise, you can see that this set is nothing but the following finite set. Right? So this set is nothing but that set where, of course, you can think of it as all the things which leave a remainder of 0 when divided by n, all the things which leave a remainder of 1 divided by n, and so on up to n minus 1. So these are also called remainder classes modulo n. Natural terminology. Okay, so that's that. What else do I want to say here? I think that's enough for at least the definition of this guy. But there is an algebra on it, which is just a reinterpretation or an avatar of modular arithmetic, nothing more than that, but it will be convenient. So the algebra on Z mod nz, we can define an addition function and a multiplication function on this. How is it defined? So we map a plus nz, comma b plus nz to a plus b plus nz. Now, one thing I should have mentioned in the previous slide, here this plus, even though it looks like your ordinary addition of integers, it is not. It is something like it's not supposed to be anything. I hope you understand what I'm trying to say. This is a set, this is a number, so it really doesn't make any sense to add them. So this whole thing is just a notation where this plus is a good, it's a good symbol to be put there, because if you look at the definition, you will appreciate the presence of this plus. But here this plus denotes the ordinary addition of integers. A and B are integers. So here when we wrote a plus, we meant the ordinary plus. But this plus is a notational plus. I hope you understand. And one more thing, nobody is going to, denote this addition function this way. As usual, if you know about fields, which I'm assuming you do, the more practical way of writing the same thing is the following. So this thing plus that thing is defined to be, you add a and b, and then write plus nz. And here already there is a well-definedness problem, because a plus nz is also equal to so many other things. A plus nz is equal to a prime plus nz whenever a prime is congruent to a modulo n. So on the face of it, it seems that a different person who writes a plus nz as this might obtain a different value here, but that's not going to happen. That's your exercise. So the well-definedness of this is an exercise. It's a very simple exercise. Okay, and this is capturing modular arithmetic, or the addition part of modular arithmetic, as I'm sure you understand. Okay, so yeah, so this is just a convenient or more natural practical notation for this horrible thing. And similarly, we have products. So we can also multiply things in Z mod nz. So here a plus nz comma b plus nz, you can guess maps to, just multiply a and b in the natural way and then write plus nz. That's the definition, and as usual, the more natural way of doing this is the following. The more natural notational way of doing it, there is nothing, we are not doing anything different. Okay, so there is an addition here and there is a multiplication on this object. Just like we have in an abstract field, we also have on this concrete object, and it enjoys a lot of properties, a lot of very natural properties, which we saw in fields also. Before I write down those properties, okay, fine. Let me just directly write down the properties. So the first thing is associativity. So addition and multiplication are associative, which is exactly the same as we wrote for fields. This is for each alpha, beta, and gamma in Z mod nz, and similarly for multiplication. We suppress the dot. Let's suppress the dot, as is common practice. We don't write the dot. Great. Commutativity, the same thing as we saw in fields. Alpha plus beta is beta plus alpha for each alpha and beta, and same for multiplication. And additive and multiplicative identity. So here maybe I'll explain a little bit. So if I write 0 to mean, let's define 0, let me write it above. So we define 0 as, when we write the symbol 0, what I mean here is 0 plus, or I just mean nz. And if you are uncomfortable, let me write a bar on top. It's also common practice to write bar on top. So instead of writing a plus nz, once n is clear from the context, we just write a bar. So that's a convenient notation. I should have mentioned it, but anyway, I'm mentioning it now. So 0 or 0 bar in context denotes nz, because 0 of course also can be used to denote the additive identity of z, but in context you understand. And just so that we are not going to confuse, I'm putting a bar on top. So 0 bar means this guy, and you can verify that 0 bar plus alpha equals alpha for each alpha in z mod nz. Very easy to verify. Similarly, we define 1 bar. 1 bar is 1 plus nz. Just a notational thing. And you can easily verify that 1 bar times alpha is equal to alpha for all alpha in z mod nz. Okay, very simple. And additive and multiplicative inverse. So if alpha is, let's say, a plus nz, or a bar, maybe I'll write a bar, then note that, or how should I say it? Then, or let me just write it this way. Observe or note that a bar plus minus a bar, this is equal to 0 bar for all integers a. So what happened? A is an integer, so a bar is an element of z mod nz. Minus a is an integer, so minus a bar is also an element of z mod nz. And if you add these two things, right, this addition is now happening in z mod nz, this will give you 0 bar. Very simple fact. Okay, and as usual, we will write this as minus a bar. So maybe I'll also make a point here. This thing will be written as that. So this is a notation. Here, this equation is a notational thing. There is no mathematical content here. Another way to write the same equation is minus a plus nz is minus a plus nz. This is just a notational thing. Okay, so just verify this, and that shows that there is additive inverse available for every element in z mod nz. So here, yeah, so this is for all integers a, but this equation is really saying that for each element of z mod nz, there is something which you add to it will produce 0. But what about multiplicative inverse? Multiplicative inverse does not hold, not necessarily. Let me scratch this out with more impunity. Multiplicative inverses do not necessarily hold. Why is that? For example, this merits an example. So multiplicative inverses do not hold for non-zero elements, may not exist. To see an example, 2 doesn't have, or I should say 2 bar doesn't have, or let me write the full thing. So 2 plus z mod 6z does not have a multiplicative inverse in z mod 6z. The reason is very simple. The reason is, if it were the case that 2 plus z mod 6z times something a plus z mod 6z is 1 plus z mod 6z, if this happened for some a, then what does that mean? It means that 2 times a is congruent to 1 modulo 6, right? This equation is exactly the same as saying, let me maybe write it in a more visible font. So if suppose you had an a such that 2 plus z mod 6z times a plus z mod 6z is 1 bar, then by definition this means 2a is congruent to 1 modulo 6. That's exactly how multiplication in z mod nz is defined. This thing is same as 2a plus z mod 6z, and now saying that 2a plus z mod 6z is equal to 1 plus z mod 6z is saying exactly this, right? But this cannot happen, because if this happened, then 2a plus 1, sorry, If this happened, then it would mean that 2a minus 1 is divisible by 6. In particular, therefore, 2a minus 1 would be divisible by 2. Anything that is divisible by 6 is divisible by 2. But this is clearly not divisible by 2. So that's it. I'm sure you noticed once, since I'm assuming that you know about inverses in the context of modular arithmetic, you should be able to see that the elements in Z mod nz which admit a multiplicative inverse are precisely those whose representatives are relatively prime with n. So these things are called representatives. If you have a plus nz as an element of Z mod nz, then a is a representative of a plus nz. So any equivalence class, suppose you pick an equivalence class under any equivalence relation, the elements of the equivalence class are called the representatives of the equivalence class. And a plus nz is a particular equivalence class of Z mod nz, a particular equivalence class under the congruence relation modulo n. So it is natural to call the elements of this thing as representatives of it, right? And a therefore is a representative of Z mod nz. Sorry, what am I saying? A is a representative of a plus nz. So anyway, all I'm saying is that a plus nz has a multiplicative inverse in Z mod nz if and only if a is relatively prime with n. This is basically the theory of inverses in the context of modular arithmetic, and a reason for it is Bezout's theorem. All right, wonderful. Finally, distributivity. So this holds. Distributivity holds. So this means that alpha times beta plus gamma is alpha beta plus alpha gamma for each choice of alpha, beta and gamma in Z mod nz. So this might be an overwhelming slide, but since you've done linear algebra, this kind of thing shouldn't scare you at all. And here maybe you should stay a little bit. If this makes you uncomfortable, then stay on it, fight with it. Also notice that all of these properties, this is exactly the set of properties that are also satisfied by the addition on integers. Associativity, commutativity, additive and multiplicative identity, the existence of additive inverses, and distributivity. This is exactly the list of things that are also satisfied by integers. So this folded world, this I would refer to this on several occasions as a folding of the integers. If you looked at the recapitulation video, I even drew a picture of it as a cycle of sorts. So this folded world of integers, or this coarse-grained view of integers, behaves a lot like integers in its algebra. So it's not a field in general. For an arbitrary n, this object Z mod nz under these natural definitions of addition and multiplication is not a field. Okay, and yeah, as we said, it becomes a field. It would become a field if every non-zero element had a multiplicative inverse, but we have a characterization for which non-zero elements have multiplicative inverses, right? Those which have their representatives as relatively prime with n. And this is the key observation which leads to the following central piece of this lecture. Finite fields. So finite field is a field which has only finitely many elements, which is finite as a set. Right? A field is a triple. It is a set with an addition and a multiplication with certain properties. So if you throw away the addition and the multiplication and only retain the set, if that set is a finite set, then you call the field a finite field. It's a natural definition. Now the question is, are there examples of finite fields? Yes, there are. So here is the, or at least a prime example of a finite field, no pun intended. Fix a prime P, then we claim that this thing is a field. We've already discussed an addition and a multiplication on it. And we've already seen all the properties that Z mod nz in general satisfies. The only thing that it needs to satisfy to become a field is the existence of multiplicative identity for every non-zero element. And that indeed happens because of Bezout's theorem. So let me maybe write down a few lines. So let a plus pz be an element of Z mod pz, and assume that this is a non-zero element. So this is not the same as 0 bar, which is same as saying this is not the same as pz, right? Want to show that this guy has a multiplicative inverse, that is, want to show that there exists some integer b such that a plus pz times b plus pz is 1 plus pz. That's what we want to do, which is equivalent to showing that ab plus pz is equal to 1 plus pz, which is equivalent to showing that ab is congruent to 1 modulo pz, modulo p. So we have just unraveled the definitions, nothing. So far, no mathematics has been done, right? We picked a non-zero element in z mod pz. A plus pz is a non-zero element means what? What is the zero element of z mod pz? Pz. This was the additive identity. Zero element means additive identity. This was the additive identity of z mod pz. So if we pick something different from the additive identity, we want to show that there is some multiplicative inverse available for it, which means to say that this equation is satisfied for some integer b. Just unravel the definitions, which is equivalent to saying this. So we want the existence of such a b. Now, since we are given that this is the case, this already tells us, or this in fact is equivalent to saying that p does not divide a. This equation, or rather this inequation, this what should I say? Yeah, this inequality or this non-equality, inequality means something like that. This non-equality just says that a is not congruent to 0 mod p, which means that p does not divide a. But if p does not divide a, then p is relatively prime with a, or a is relatively prime with p. Right? So that much we know. But once a is relatively prime with p, this means that by Bezout's theorem, there exist integers b and let me say y, such that ab plus py equals 1, right? If GCD of two integers is 1, then you can find two other integers b and y such that ab plus py is 1. That is Bezout's theorem, or I think it is also referred to as Euclid's theorem in some references. And now once you have this, this is exactly saying that ab is congruent to 1 modulo p. So that finishes the proof. This is what we wanted to prove, but that is available to us. So we have an example of a finite field. Clearly, this is a finite set. What is the size of this guy? The size of this guy is p. The size of z mod nz is n. The size of this guy is p, therefore. So let me maybe write this somewhere. The size of z mod nz, as we saw in the previous slide, is n. So for each prime p, there is a field of size p, and that is this field, z mod pz, with the addition and multiplication that we discussed. All right, so let's look at the most simplest example of this thing. It's f2. What is f2? f2 by definition is z mod 2z, which is of course 2z comma 1 plus 2z, right? That's what this set is. So this is the set of all the even numbers, and this is the set of all the odd numbers, right? 2z means what? Those things which are divisible by 2, so all the even numbers. And 1 plus 2z is you're offsetting every even number by 1, so all the odd numbers. And clearly, I mean, 2 is a prime, so it checks out. It's a field, but let's maybe explicitly write down what these, what the algebra here is. Before we do that, let me write this as 0, not even as 0 bar. I'll just write this as 0 as is common practice. And I'll write this as 1. I won't even write this as 1 bar, just 1. So what is 0 times 0? It's 2z times 2z, so it is 2z and hence 0. 0 times 1 is also 0. 1 times 0 is 0. And what else? 1 times 1. This is 1, right? 1 plus 2z times 1 plus 2z is 1 plus 2z. So we have that. And for addition, 0 plus 0 is 0. And you can fill it up. 1 plus 1 is 0. So this equation may look weird, but of course, if you know the meaning of the symbols that are present here, it's no mystery. I do not mean to say that this 1 is your integer 1. 1 is not an integer here. So this abuse of notation is rampant and encouraged, right? Most of the time, f2 is just written as 0, 1. This is how people write it. All right, so that's the simplest example of a finite field. And now let us discuss more. There is more to say about finite fields. One can ask the question as to, are there other finite fields with a size p? So this is one such field. This is one, fix a prime p, you can create a finite field of prime size. Maybe there are other finite fields of prime size fundamentally different from this one. One can ask such questions. And also, can we characterize finite fields? What are all the possible finite fields? Those questions are natural. We won't be addressing them in full generality here, but we will maybe give a glimpse of the true answer. All right, so let's proceed. Right, so let's look at an example of a finite field of size 4. This is not a prime, but still there is a finite field of this size. And I mentioned this as a bonus example because this looks horrendous and the theory behind this construction will not be explained here. I will maybe give just a little bit of a glimpse. So F is a 4-element set where 0 and 1 are two symbols. Just think of them as two different symbols, and alpha beta is two other extra symbols. And the algebra of 0 and 1 is exactly the same as it was in the previous page. So that is preserved, but there is some additional stuff here which also behaves with 1 and 0 and with themselves. So all the other rules are written here. So this is the way alpha and beta behave with 0 and 1. This is the definition, right? We are defining an addition on this set. All these are definitions. We define 0 plus 0 as 0, 0 plus 1 as 1, and so on. All of these equations are definitions. So this is how addition is defined and this is how multiplication is defined. I'm just claiming that with this definition of addition and multiplication, you get a field, right? And you can verify that if you have a lot of time. And you might be right in thinking that maybe some illegal substances were involved in construction of this example. But the way this has come about is the following. The way this has come about is, note that this polynomial, whatever polynomials mean, I don't know if you know about polynomials, but for the moment just play along. If you don't understand what I'm saying, fine. So this is a polynomial. Think of this as a polynomial over f2. f2 is your field. It has some, it has some elements in it. And I'm sure you've seen minimal polynomials, etc. in your linear algebra. So this shouldn't feel all that foreign. We do have polynomials over abstract fields when we discuss linear algebra. That is how you develop the full theory of eigenvectors, etc., eigenvalues, eigenvectors. So this is a polynomial over f2, right? So this one is not your usual one. It is the one that is present in f2. Just look at the previous slide. And now this polynomial does not have a root in f2. At the very least, it does not have a root in f2, because if you substitute 0 in place of x, you get 1. And if you substitute 1 in place of x, what do you get? You get 1 plus 1 plus 1. But this is equal to 1 because we are working in f2. So this is equal to 1. So there is no root of this polynomial in f2. And in fact, what is a stronger statement, or a seemingly stronger statement is that this is an irreducible polynomial over f2, whatever that means. And now what you can do is you have the set of all the polynomials over f2. I'm not assuming you're familiar with this object just yet. Later we might explore this or discuss this later. And then you kind of quotient out by all the things, or the or quotient out by all the multiples of this polynomial. All of these words you may not know at all anything about. I'm not assuming that you know, but I'm just trying to explain where all this comes about. So the fact that this is a degree 2 irreducible polynomial and the fact that f2 has size 2 means that the quotiented object, whatever that quotiented object is, that quotiented object has size 2 to the power 2. Okay? And that's how this example was constructed. The real discussion here happens in the context of Galois theory. So if you read Galois theory, or if you know Galois theory, then you already know what I'm talking about. but let this be an invitation to Galois theory. Okay, so don't worry about this example. This is just a bonus example. You can totally ignore it, no problem. I'm just trying to say that there do exist exotic fields. All right, let's proceed. So now we want to discuss a certain notion associated to any finite field, or in fact any field, but it really rears its head in the context of finite fields. So we will define a certain operation on fields first. Suppose you have any field, abstractly any field at all, then for any integer n and for any element x in your abstract field, we define this thing which is read as n dot x. Let me write that. So this is read as n dot x, as you just sum up x n times, but n might be negative, so we have to fuss a little bit. So if n is positive, you say x plus x plus x n times. 0 if n is 0, and minus n dot x if n is negative. So if n is positive, let's say n is 2, then n dot x is just, or 2 dot x is just 2 dot x is just x plus x. If n is 0, then 0 dot x is 0. So this 0 is the 0 of the field. The 0 here is in integers, but the output is in the field. Okay? And if n is negative, let's say minus 2 dot x is what we are talking about, then what you do is first you find out what is 2 dot x, which is x plus x, and then you put a minus against it. So this minus here, this minus is the minus in the field, like, right? This element is the additive inverse of this element in F. Okay? And I can already hear you complaining. What have we done? We have defined a function of this sort, right? We have defined a function of this sort, and it kind of behaves like multiplication. We will see. And the notation we have chosen here is dot. What is the notation have we chosen for the multiplication of the field, which is a function of this sort? We have chosen dot. What is the multiplication that we usually what is the notation for the multiplication that we have on our usual objects like r, z, c, q? It's dot. Every time we use a dot. So that might cause confusion in your head as to what exactly is this. Don't get confused. We are defining something new. It's convenient. It's just a notation. And I've just somehow, I'll try to make a fat dot here instead of your tiny dot. I would also not like to omit this dot. When we are multiplying two things in the field, if x and y are from the field f, then xy is just a shorthand for x dot y, because it takes a lot of time to put a dot, right? But this dot I wouldn't want to omit, but if I omit, I'm not going to apologize, because I apologize now. Okay, so all that rant was to placate you, and now note that. And so this is the definition. There's nothing to note here. I could have said, maybe it's a better thing to write, that this is nothing but minus x plus minus x, or maybe I'll write n dot minus x. That's better. It's just n dot minus x. Verify. This is an exercise. Minus n dot x by definition is minus of n dot x, but just verify this thing is same as that thing. All right, and also verify that for any two integers m and n, we have this kind of a distributivity of sorts, right? So this is a fat dot. Very simple things, nothing complicated going on, just a notation. And now with this notation in hand, we can prove that if we have a finite field, then there is a unique prime p for which p dot 1 is 0, where of course this 1 refers to the multiplicative identity of the field. Okay? Think about it. It's an interesting fact. Think about it. Let me give a proof, but I encourage you to pause the video and find your own proof. That's the best way. All right. So consider the numbers, not the numbers, but consider the field elements. 1.1, very confusing, right? This is just, what I mean is when I read 1.1, I meant 1 as an element of integers and 1 as an element of the field. Okay, so consider 1.1, 2.1, 3.1, and so on. Right? So these are infinitely many symbols, infinitely many, or in an infinite list of elements from F, right? But F is finite. So in this list, there has to be repetition, right? So there exist two integers. Without writing all of that, by pigeonhole principle if you want, there exist two integers, m and n, which are distinct, such that m dot 1 equals n dot 1, right? Since this is an infinite list of only finitely many things, there has to be repetition, which is written here. This is same as saying that there is repetition. All right, great. But this means what? This implies, let's say n is greater than m. I'm just without loss of generality assuming that n exceeds m. They are distinct, so one is bigger than the other. No harm in saying that n is greater than m. So this implies that n minus m dot 1 is 0. Right? Either you can use this or you can use common sense. What is this? This is 1 added m times and this is 1 added n times. We are just saying cancel off these m1s with m1s on the right hand side. You will be left with n minus m1s on the right hand side and you get this equation. But if you don't like that idea, you can use this, right? So we have that, just verify. And now, so far what have we shown? That there is a non-zero positive integer which dots 1 and gives us 0. I might even call it scaling because that's very natural. This is really like your scaling function. We are scaling elements of f by integers. So there is some non-zero integer, in fact a non-zero positive integer, which scales 1 to produce the 0 of the field. Okay. So thus, the set of those positive integers, k is positive, with this property is a non-empty set. So far, this reasoning just tells us that this set, the set of positive integers which scale 1 to 0, is non-empty. Right? So this is a non-empty subset of natural numbers. Positive integers are precisely natural numbers. So this is a non-empty subset of natural numbers, and hence by the well-ordering principle. The well-ordering principle says that we can find, or in fact, there is the smallest element in it. So thus by the well-ordering principle, let, what's a good symbol for an integer? Let me write h. So h be the smallest element in this set, be the smallest positive integer, such that h dot 1 is 0. So this part was a bit extraneous. I was just trying to be very, very formal. We have found a positive integer which scales 1 to 0. So there naturally is a smallest positive integer which scales 1 to 0. That is all that I'm saying. This whole thing is just to, I shouldn't have maybe. Anyway, so there is a smallest positive integer which we have denoted by h, which scales 1 to 0. We claim that it is a prime. Claim right? And in the proof of this claim, I want you to do this exercise that m times n dot x equals m dot x times n dot x. This dot is our scaling dot. Here it is your usual multiplication of integers. and here the multiplication is happening in the field. And this is for all integers m and n, but it should be very clear for positive integers immediately. If m and n are positive integers, on the left side, you're adding x mn times. And on the right side, first you add it m times, then you add it n times, and you multiply the two bracket, you will get mn times x written and added. So this should be very clear for positive integers, but for negative integers, you'll have to worry just a little bit. It's a very simple exercise, just like that one. So now to prove h is prime, if it is not prime, if h is not prime, then we can write h as a times b, where a and b both are greater than 1. So since h dot 1 is 0, we get ab dot 1 is 0, which gives us a dot 1 times b dot 1 is 0. But then, since we are working with a field, either this is 0 or that is 0. One of them has definitely have to be 0. But if a dot 1 is 0, note that both a and b are strictly smaller than h, and both are positive integers, but both are strictly smaller than h, right? But that would contradict the minimality of h. If this is 0, that would contradict the minimality of h, because a is strictly smaller than h and a positive integer. Similarly, if this were 0, we would have a problem. So this equation simply cannot hold. That would be a contradiction. So that finishes the proof that h is prime. So what we have shown is that there does exist a prime which satisfies this equation. Now we want to establish the uniqueness of the prime. So for uniqueness, maybe I'll write here. Suppose we have two different primes which satisfy that equation. So if p dot q is 0 and q dot 1 is 0 for two distinct primes p and q, maybe I'll transfer everything to the right hand side because there isn't enough space. So for uniqueness, suppose we have two distinct primes p and q, then by Bezout's theorem, since p and q are distinct primes, they are relatively prime with each other, we can find integers x and y such that px plus qy equals 1 for some integers x and y, and thus p dot x, sorry, what am I writing? Px plus qy dot 1 is equal to 1 dot 1, which implies px dot 1 plus qx dot 1 is 1. So this equation was written in integers, but this equation is written in the field. This one that you see here is a field element, the multiplicative identity of the field. All right, now what about this guy? This guy is nothing but x dot p dot 1, correct? This guy is x dot p dot 1. Yeah, maybe I should even mention that. So here is your another exercise. Mn dot x is also equal to m dot n dot x for each pair of integers m and n. So all I'm saying is that this is equal to that. Another simple exercise, nothing going on. Okay, so this thing is x dot p dot 1, and similarly that thing is x dot q dot 1, but p dot 1 is 0 and q dot 1 is 0. So the left side is 0. So what we have a field where the multiplicative identity is same as the additive identity, because this is 0. So the multiplicative identity is same as the additive identity, but that doesn't happen in a field. So we are assuming that every field that we have is of size at least 2. I mean, you can argue that if you have a field where you have only one element, namely the element 0, then the additive and the multiplicative identities coincide. So let me just make this convention that when we say a field, we mean at least 2 elements.
Okay, so that's a contradiction. If we had two distinct primes with this property, we would have a contradiction. So the uniqueness is already, if at all a prime exists, it has to be unique. And a prime does definitely exist, we have shown. So I spent a lot of time on this slide. The best way would have been to just prove it yourself. That would be the quickest. Now, having proven this lemma, we can define the characteristic of the finite field. So what is it? It is this unique prime. And we will denote this as char f. All right. And before we proceed, I want to prove one more property. And to prove that, I will give you another exercise of this nature here. What is the exercise? We just need to show that for any two field elements x and y, we have the following is true. X and y are the field elements, so this product is happening in the field. And this is the scaling by m. Let me write n instead of m, doesn't matter. Right, and we just want to show that this equation holds for all integers n and for all field elements x and y. And you can see this immediately if n is positive. Say for example n were 2, then what is the left hand side? It is xy plus xy, which you can write as x plus x times y, right? Which is just 2 dot x times y. So again, it's a triviality. And now based on this, I want to mention one final thing on this slide, which is that suppose P is the characteristic of our field, then I want to say that P kills everything. This is what I want to say. It's a very simple thing. Here is the reason. If x is 0, then clear. So suppose x is non-zero. And if x is non-zero, then it has an inverse since we are dealing with a field. So there is some y such that x times y is 1. Right? And now this tells us that p dot x times y is 0, because p dot x times y is p dot 1, which is 0. So I'll just skip a step and write 0 here. All we are doing is we are dotting with p on both sides. But this p dot xy we will write as, p dot x times y. Right? This thing, sorry, the left hand side we are writing like this. I'm just using this property. And therefore p dot x must be 0 because y is non-zero. To be very formal, what you are doing is if you multiply this equation by y inverse on both sides, it said another way, you are multiplying this equation by x on both sides because the inverse of y is x. So you get p dot x is 0. But anyway, in a field, if the product of two elements is 0, then one of them has to be 0 and here y is non-zero. So p dot x has to be 0. So anyway, this is a simple fact. And with this in hand, let us proceed. So this is the last slide. And here we want to prove something very interesting. Suppose f is a finite field whose characteristic is this prime p. We will talk about the size of we want to make a comment on the size of this finite field. And to do that, first we will prove a structural statement. What we will do is we will endow f with a vector space structure over this field. F itself is a field. F is not a vector space over anything as of now. Well, f is a vector space over f because every field is a vector space over itself, but that's not interesting. What is going on is somehow we will think of this field as a vector space over something else. Even though it is a field, it will simultaneously be a vector space. That's very nice. Okay, and then we will comment on the size of f. So here is how we will endow f with a vector space structure. So f already comes with an addition, right? F is a field, so it has an inbuilt addition in it. We will use the same addition, and to give it a to give it a vector space structure over z mod pz, we need to define a scaling function, right? We need to define a function of the sort z mod pz cross F to F. Right? If you want to give this thing a vector space structure over this field, we need to define a scaling function of this nature and show that it behaves well with the addition. So the addition on F is the same addition we will use. We will not define some new addition. Okay. So what is this map? This map is very simple. This map is just take A bar. So A bar is A plus PZ. A bar is just a shorthand for A plus PZ. So A bar comma X, or maybe I will not write it this way. I will write in a different way. I will write A bar scaling X is defined as A dot X. Now you may be very confused at this point. This dot is what we are defining. This dot is this dot. Again, dot is very abused, but what can you do? So we are defining this guy, and this is nothing but the image of the pair A bar comma X under this dot. So this is how we write it, right? And this dot is what we defined earlier. A is an integer. So this is for all integers A. This may look very confusing, but it is not. Fix an integer A, you get an element of Z mod PZ, and now we are defining the scale of X by that element of Z mod PZ. How do we define it? We are defining it as the scaling of X by the integer A. In the previous slide, we defined scaling of any field element by integers. So this is legitimate. This is legitimate because of the previous slide, and this is what we are defining. Now here there is a question of well-definedness, because A bar could very well be equal to B bar for some different integer B, and then some other person might write this as B dot X for some other integer B. So why should the two things be equal? So there is a well-definedness issue, and one thing which I erased I want to write down. So this again recall is A plus PZ. Okay, great. So for well-definedness, just note that if A bar is equal to B bar, then this is equivalent to saying that A is congruent to B mod P. Correct? And therefore, A is equal to B plus PK for some integer K. And therefore, A fat dot X equals B plus PK fat dot X, which implies A dot X is B dot X plus PK dot X. And now by the basic properties of dots that we have proven, this thing can be written as K dot P dot X. And now since P is the characteristic of the finite field, this is 0, right? This is the last property that we saw in the previous slide. So this is 0, and therefore A dot X is equal to B dot X. So what we have shown is that whenever A bar is equal to B bar, A dot X is equal to B dot X, which means what? Which by definition of the scaling means A bar dot X is equal to B bar dot X. Let me not use a fat dot in the scaling here. This is just a simple dot. This is the fat dot from the previous slide. Right, so this solves the well-definedness issue. So there is this well-defined scaling function, and now this is your exercise to check that F indeed becomes a vector space over Z mod PZ. So now this particular triple F plus and the scaling that, I mean, if I write a dot, it will become confusing because this dot may refer to the dot that the field comes with, but this dot refers to this dot. So let me not write it. So this triple, or there is no triple that I'm writing, but you know which triple we are talking about. So this scaling operation now converts F into a vector space over Z mod PZ, but that has to be checked. Right? Various axioms of vector space has to be checked here. Which one should I show you? And there are some 8 axioms that one has to check. So no, so I'll just write check that this actually gives you a vector space. Okay, wonderful. So this is a vector space over Z mod PZ. And now we want to say that the size of our finite field is some power of P. There is some positive integer K such that the size of F is the corresponding power of P. Why is that? Well, since F is a vector space over Z mod PZ, under our definition of scaling, it has some basis. And since F is finite, this basis has to be finite. So let the dimension of F as a vector space over Z mod PZ be equal to K. Then there is a basis of size K. So let maybe E1 up to EK. Maybe I'll write X1 up to XK. Form a basis. Be a basis of F over Z mod PZ. And thus F is precisely the following set. It is, what's the best notation? Let me write bars A1 bar X1 plus dot 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 A K bar XK, where AI bar are from Z mod PZ arbitrarily. So that's precisely the set F, right? This is the span of the basis, and therefore that is same as the vector space. Further, since X1 up to XK forms a basis, for distinct choices of A1 up to AK, you get distinct vectors. You cannot get repetition here if you disturb things here. So therefore, there are P choices here up to there are P choices here. There are K slots, and in each slot you can enter any of the P values, and therefore you have P times P times P times P up to up to K times. So you have P to the power K elements in F. Another way to say was, since the dimension of F is K, we know that F is isomorphic to the base field to the power K. If a vector space or a field, suppose we have a vector space or a field, what's a good name for a field? I don't want to use F. Suppose you have a vector space or a field K, then if dimension of V is N, then V is isomorphic or has a linear isomorphism to K power N, right? Here K is actually Z mod PZ and V is actually F. So it's a bit perverse notationally, but conceptually also it's somewhat mind-boggling because you're seeing it for the first time. But it's not. It's a beautiful piece of reasoning. Like, amazing. I love it. Okay, and finally, so we have proven this lemma. This lemma is fine. So what this says is that you cannot have finite field of arbitrary sizes. Every finite field has size prime power, although it is not clear if every prime power is obtained as the cardinality of some finite field. Maybe there is no field of size 9, who knows? Maybe there is no field of size 64, even 64 is prime power, certainly. So maybe there is no such field, but no. So there is a fact in field theory or Galois theory that for each prime P and for each positive integer K, there is essentially a unique, whatever this means, unique field of this size. And we won't get into this construction. This is in a separate course when we discuss Galois theory, which is going to be far in the future, I think. There we will discuss these things. Yeah. So for us, the takeaway is that Z mod PZ is a field. This was not really necessary for us in this course, but yeah, I wanted to do it. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.